Good afternoon, everyone. Good afternoon. Hope everybody's doing all right. Everybody's doing okay. Hope everybody had a great weekend. Looks like everybody is in. All right. If I'm not mistaken, last class we closed out chapter 5 with 5.4. So we should be looking at 6.1 today. Let me go ahead and let somebody in. And of course, feel free to let me know if I got it wrong. So we'll go ahead and get into chapter 6 notes, and then from there, see if anybody have any questions. All right. Yep. And of course, my notes not popping up. All right. So we're looking at 6.1. We may knock out 6.2 today as well. I think 6.1 is short, but 6.1 discrete random variables. Write that random better. Discrete random variables. So a random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. They are typically denoted by using capital letters. So then we have two types of random variables we'll get into in a second. Just want to give people a chance to copy. All right, the first one, discrete random variable, has either a finite or countable number of values. Can be plotted on a number line with a space between each point. So in other words, when you're talking about a finite number and an actual number, if you can actually count it and there's no discrepancy in it, you'll see what I mean when we look at the other type. In other words, if there are 5 people in the classroom, there are 5 people in the classroom. There's not 5.5 people in the classroom. Or in other words, there's not 5.1, but it also could be 5.12 or 5.13. And if you round it, it'll still be 5.1. Like if there's no discrepancy, it's either 5 people or it's not. Or, saying if that number is definite or finite, then that's considered discrete. Continuous random variable has infinitely many values. So a lot of times when you're talking about something continuous, a continuous random variable is something that's being weighed or measured. So in other words, if I was weighing, if I weighed myself, let's say I weighed 165 pounds, if I had a more accurate scale, it would also be correct if I weigh 165.1 pounds. If one scale goes to just the first ones place, but then another scale goes to the tenth place, both of them would be correct. Or if another one goes to the hundredth place, all 3 of them would still be correct. It's just that one is more accurate than the next. So that means I have infinitely many values that would be considered still correct. Going back to my previous example, if it's 5 people, it's 5 people. There's no such thing as a 5.1 of a person. So that's the difference between discrete and continuous. Discrete has an actual number, and there's no deviating from that number. But continuous, there are infinitely many ways that you can represent that answer. And that can be plotted on a numbered line in an uninterrupted fashion. So first example that we're going to look at is, being able to decipher between the two. You know, is it discrete or is it continuous? Give a few examples to make sure we're okay with the difference between the two. All right, is everybody okay with scrolling up? All right, so discrete or continuous. The number of A's earned in a section of statistics with 15 students enrolled. So this one, there's a solid number on that. So that's why that would be considered, discrete. Um, if 5 people earned A, then 5 people earned A. And there's no deviating from that. And that's, that's all there is to it. If you can look at a number and say that that number is what it is and there's no other flexibility on it, then that number is considered discrete. If it's a finite number, if it can be counted, and then that's just the number, that's the only answer for it, then it's considered discrete. Looking at B, the weight of a sandwich at the deli, that will be considered continuous. And like I said, whenever you're dealing with weights or scales or measurement, a lot of times that's going to be continuous for you because you can always have a more accurate scale that will still represent the correct weight of that sandwich. So it can be 5 grams, it can be 5.1 grams, 5.13 grams, 5.137 grams. You can always go that next digit and still be correct with your answer. The number of cars that pass through a McDonald's drive-through in the next hour. So the number of cars that pass through the drive-through at McDonald's in the next hour, that will be discrete. If it's 10 cars that pass through, then it's 10 cars that pass through. And that's the only, legitimate answer for that. It's either 10 or it's not. And then the last one, the speed of the car that passes a state trooper, and that will be continuous. Because once again, it's measurement. The accuracy of the gun, will dictate how precise your answer is. But that doesn't mean that it is going to be incorrect. So you can represent that answer in multiple ways.
So would example D be continuous because of the way that the value is measured?
Yes. Mm-hmm. Yeah. So basically, whenever there's a measurement, you know, involved, for the most part, it's going to be continuous. It's hard to find an example in which a measurement couldn't be looked at continuously, because if you have a weight, scales, anything of that nature, you can always, like I said, go more precise and I'll still represent the same answer.
That makes sense, thanks.
Yep, not a problem. Anything else, anybody else before we scroll up? All right. All right, the next thing, probability distribution. Probably could that a little better. Probability distribution of a discrete random variable x. Provide the possible values of a random variable and the corresponding probabilities. All right, so rules for a discrete probability distribution. Seen these rules before. The sum of all your probabilities, at least I think so. I know at least number two. The first one, the sum of all of your probabilities have to add up to 1. That's what that notation means right here. Sigma, that means the sum of, or adding up all of your probabilities. Well, the sigma means adding up, and then what follows, it tells you what to add up. So here, it lets us know we're adding up our probabilities. So adding up all the probabilities have to add up to add up to 1. And then each one of your probabilities have to be in between 0 and 1 inclusive. And of course, it is possible for something to be a 0%, 0% chance of happening. Also, 1 would be 100%. But those two rules have to be in place for it to be a discrete probability distribution. All right. So we're going to look at these two charts, and we want to determine which of them follow the discrete probability distribution. Where they got the numbers from and all that, that's not our concern. In this case, we just want to know, does it fit the criteria that has to be met in order to describe a discrete probability distribution? So in other words, does rule 1 and rule 2 take effect or hold true in each one of these examples? If they do, then it will represent a discrete probability distribution. If either one of the rules are broken, then it does not. So on the first one on the left, in all three of them, we have 1, 2, 3, 4, 5 for X. And then the probability, when you see P of X right here, that means the probability of 1 happening, the probability of 2 happening, the probability of 3 happening, 4 and 5. So down here is the probability of each one of those occurring on the left. So we have 0.20, 0.35, 0.12, 0.40, and then negative 0.7 for A. For B, 0.20, 0.25, 0.10, 0.14, 0.49 for B. Then C, 0.20, 0.25, 0.10, 0.14, and then 0.31 for C. All right, give you guys a chance to finish writing that down. All right, so let's look at the first one, and we're gonna ask ourselves, does it break any of the rules here? We have first one, adding up all the probabilities have to, that the result has to be 1, or, and not or, but then in rule 2, does each one of our probabilities, are they in between 0 and 1? So for the first one, we see that negative 0.07. So that fails rule 2. That's less than 0. So it's impossible for your probability to be negative and fit your discrete probability distribution. So A does not work for us. All right. Then B does not work for us because it fails rule 1. When you add up your probabilities together, it gives us 1.18. Remember, it has to equal to 1. Can't be less, can't be more. Any problems before we look at C? So with C, we see that each one of them are between 0 and 1 as far as the probabilities are concerned. Then you have to add them up to see if they give you 1. And we see right here that they do. So C does represent a discrete probability distribution because it satisfies both rules. Any questions? All right, here we scroll up. Oh, that's it for this section? Okay. So, one last thing. If my math lab asks for the mean of discrete random variable or the standard deviation of the discrete random variable, just like before, we mentioned before what you can do. Use a website app or calculator to find it. I forgot whether this class asked for it, so that's why I said ifs. But those two things, I'm not going to hold you accountable for knowing how to, once again, knowing how to do the formula, but you should have something reliable that can find it for you if it asks for it. Once again, easycalculation.com does a majority of the things that are asked. So, like I said, mean of discrete random variable calculator or easy calculation, and same thing with standard deviation of discrete random variable. All right. Questions. Before we look at 6.2. All right. Let's go look. All right. Binomial probability distribution. So it's a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive outcomes. These two outcomes are generally referred to as success and failure. So example of that is in basketball, success will be making a shot, failure will be missing the shot. So there's no other options on that. You either make the shot or miss the shot. So that's what we mean by two mutually exclusive outcomes. You can't make and miss the shot. They're mutually exclusive. They have no outcomes in common. You're doing either or. And success is considered making the shot. Failure is considered missing the shot. So experiments in which only two outcomes are possible are referred to as binomial experiments, provided certain criteria are met. Everybody okay? All right, so looking at the criteria for a binomial experiment, experiment is said to be a binomial experiment if, number one, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. Are you done with the black? All right. Number two, the trials are independent. In other words, the probability of one does not occur, does not, well, let me tell you this. The one event occurring does not affect the probability of another event occurring. I keep saying occurring. So the trials are independent. One event occurring does not affect the probability of another one occurring. Then for each trial, number three, there are two mutually exclusive outcomes, success or failure. Mentioned what that meant a few minutes ago. And then number four, the probability of success is the same for each trial of the experiment. Of course, let me know if I scroll up and you're still copying something. In the green, we're looking at the notation used in a binomial probability distribution. Lowercase n is the number of trials of the experiment. P, lowercase p, is the probability of success. 1 minus p would be the probability of failure. Remember, there are only two outcomes. So if p is the probability of success, then 1 minus p will be the probability of failure. And then x is going to be the number of successes in n trials. So you notice x is going to be in between 0 and n. It cannot be larger than n because the number of trials is n. So 0 is no successes, and then n would be all of them were successful. So in other words, if I had, well, I'll wait on that because we got an example that'll show that. So all right. So we're going to use that information to determine if we actually have a binomial experiment, and it's based on those four criteria. So we have determined which of the following probability experiments qualify as binomial experiments. For those that are binomial experiments, we're going to identify the number of trials, probability of success, probability of failure, and the possible values of X. All right, so A, an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. I'll give you a chance to write it down. All right, so we want to see if this experiment is a binomial probability experiment. So first thing we want to do is explore all 4 of those criteria. Now, if it doesn't meet one of them, let's say we get to number 1, it doesn't meet one, then we don't have to keep going. We just, we keep going until we see that it doesn't meet one, or if it meets all 4, then we know we have one. Okay. So first one, is there a fixed number of trials? The answer is yes, because it says, where's my pen at? Experiment in which a basketball player who is sports story made shoots 3 free throws. So that's the number of trials. Second one, are the trials independent? The answer is yes. It says he's historically, he or she, I don't think that's, oh no, it does say he. Okay, he's historically an 80% free throw shooter. So missing one shot is not going to affect his probability, his historical reference of what he normally makes. So these trials are independent. I meant to put here, are the events mutually exclusive? Um, so that's why I put that little spot right there, put events. Are the events mutually exclusive? The answer is yes. Once again, you either miss a shot or make a shot. You can't miss and make a shot at the same time. So you either missed the shot or you made the shot. If they are mutually exclusive, that means they would have some of their events in common. Like we talked about, cards. Having a king of hearts. That card is a king and it's a heart. So they have that one card in common. So here, these events are mutually exclusive. They do not have any events in common. Is the probability of success the same for each shot? The answer is yes, because he has enough history to say that he is an 80% free throw shooter. So you are dependent upon or leaning upon the idea that 80% is your chance of him making the shot. All right. Any problems with either one of those 4? Now, since it meets all 4, that means it is a binomial experiment. Any problems? Any problems? So since we've determined that it meet all 4 of the criteria and it's a binomial experiment, now we can go to the next part of the problem. It's right here. It says if it is a binomial experiment, we need to go ahead and name the number of trials, probability of success, probability of failure, and the possible values of X. All right. So here we go here. So N is going to be 3. That's the number of trials. That's the number of shots. Our trials in this experiment, the shots the person is taking. Percentage of success, probability of success is 80%. So it's going to be 0.8 for us. Move your decimal 2 places to the left. Subtract that 0.8 from 1, it'd be 0.2. So if he's an 80% free throw shooter, 80% chance that he'll make it. It's 20% chance that he will not make it, which is a failure, missing the shot. And then your X is going from 0 to N. Once again, N is 3 shots. So 0 is the, him missing all of his shots. 1 is him making 1 shot out of the 3. 2 is making 2 shots out of the 3. And then X being 3 is him making all 3 shots. So remember, X always represents the number of successes in the experiment. So if I want to find a probability of X, in this case, let's say if I want to find a probability of 0, what's the probability that he'll miss all his shots? Probability of 1, what's the probability of him making just 1 shot? What's the probability of him just making 2 shots? And then here, what's the probability of him making all 3 shots? So that's what we're saying here. When X is a specific number, what's the probability of him doing either one of those or having one of those outcomes? All right. Any questions before we look at B? All right. Scrolling up. All right. B, a probability experiment in which 3 cards are drawn from a deck without replacement. I underline that because that's key in our determination. Without replacement, and the number of aces is recorded. So remember, we want to determine if this fits a binomial experiment, binomial probability experiment. First thing we have to do though is see if it meets the 4 criteria. All right, let's look at them. So first one, is it performed a fixed number of times? The answer is yes. It's 3. We picking out 3 cards from the deck. All right. Then we get to number 2, are the number of trials or are the trials independent? The answer is no. And that's because it says without replacement. Without replacement means I'm not replacing the card back into the deck. So when I pull out, we got 52 cards. If I pull out a card, if I don't put it back, now I only have 51 cards. So now my probability changes for the next card. Because before I was pulling out from 52, now I'm going to be pulling from 51. And so that's going to change my probability. So that's what we mean by without replacement. And since it is without replacement, that means that the trials are not independent, and we can stop right here. It is not a binomial experiment because it does not meet all the criteria. All right, any questions? Any questions? All right. One more like this. Pretty good. I scroll up. All right. So C, according to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained, and the number of Americans who chose chocolate as their favorite ice cream flavor is recorded. I give you a chance to write for those who are writing it. right, so let's see if it meets the 4 criteria. So first one, are the experiments performed a fixed number of times? The answer is yes, because we have a sample size of 10. We're choosing 10 random people. Are the trials independent? The answer is yes. Choosing the choosing is random. So choosing one person has nothing to do with choosing the next person. Are the trials mutually exclusive? Yes, because you either choosing ice cream or choosing chocolate as your favorite, or chocolate is not your favorite. We're not saying that you like ice cream or you like chocolate. It's not about liking chocolate. It's about chocolate is your favorite or chocolate is not your favorite. So that's why these trials are mutually exclusive. Talking about being favorite. And then is the probability for success the same for each? The answer is yes, because they already did a poll on the population, and that probability is going to be a 28% chance that you're going to pick somebody that likes chocolate as their favorite. All right. Any questions on those before we go to the next part? All right. Can I scroll up? And this is just in the green solidifying what we already said. This experiment is a binomial probability experiment because it meets all the criteria, all the criteria. And then remember, if we found out that it was a binomial experiment, then we go ahead and label, all of our pieces of information. So N is going to be 10. That's the number of trials. 28% is the probability of success, so it's 0.28. Then subtract that from 1, that's 0.72. That's probability of failure. Don't forget, success is choosing someone that has chosen chocolate as their favorite, and then failure is choosing someone that did not choose chocolate as their favorite. And then X is the number of possible successes during your trials. So it's possible that you could choose 10 people and none of them has chocolate as their favorite. So that's what 0 represents. And then 10 is the probability of choosing, you choose 10 people and all 10 of them choose chocolate as their favorite. All right. Any questions? Any questions? All right. So here's the formula that we will use to determine the probability of what we just finished talking about. Binomial probability distribution function. So we had a probability of X. Remember, X represents the number of successes within the trials. We have NCX. That C is the combination function. Then that's P to the X power times 1 minus P to the N minus X. So I'll show you how we plug it in a second. Also, just like before, if you were to Google binomial probability distribution calculator or function, there are things out there that can calculate stuff if you have the proper information. So feel free to use that. You can also put this stuff in your regular calculator. Just takes a little know-how. And most definitely, if you have any questions on how to use your calculator, feel free to get with me, and I'll do whatever I can to help you out. All right, let's scroll up. All right, so according to CTIA, 41% of all U.S. households are wireless only households. That means no landlines. Let me make that a little closer. No landlines. So in a random sample of 20 households, what is the probability that exactly 5 are wireless only? So let you guys write that down, and then we'll get to it. All right. So let's look at exactly 5 are wireless only. So you're choosing 20 households at randomly. Out of the 20, 5 of them were wireless only. 5 only had landlines. So the first thing we want to establish are our variables. So P is going to be 41%. That's where we got from right here. So 41% of all U.S. households are wireless only, no landlines. And then the probability of not getting a wireless only home is 59% because you subtract that 0.41 from 1. Number of trials is 20, random sample of 20. And then X is always going to go from 0 to N. So in this case, 0 to 20. So any questions on that before we go any further? It's just us establishing the given information. All right. So now if I choose 20 households randomly, and I want to know out of those 20, what's the probability of exactly getting 5 that are wireless only? This is how I would do it. This is the formula right here. Remember, we going back to this setup, and we established what N, X, and P are. And that's what we did right here. Plug them in accordingly. So N is 20. X for this, in this case, is 5 because we want to know 5 successes. So X is 5. P is 0.41. Here, if you just wanted to go ahead and put the 0.59, you could. I mean, that's what I ended up doing anyway. But I just went ahead and plugged it into the formula so you see what exactly how the formula is giving us. But it's 0.49, 0.59, excuse me. Once again, 5 is X. And then this is N minus X. And that'll give us 15. So now, if you have a calculator, scientific calculator, you can put it in this way. And notice the symbolism, the symbols that I've used, parentheses, the hats, to raise stuff to the exponent, the combination versus permutation formula right there. So notice we don't substitute anything in for C. That's an actual formula. And like I said, this is how you put into your calculator. And certain calculators have extra buttons. They have stuff like this where you could raise it to your exponent that way. You wouldn't have to use this symbol. But every calculator is different. So if you have any questions on your calculator specifically, then make sure you get with me on that. All right, so once you plug into the calculator, you get this right here, 0.0656 or 6.56%. Any questions? All right, so we talked about this before. In my math lab, you could get a sentence answer. And so one of the ways you could get an answer in this, dealing with this type of problem in 100 trials of this study, and that means if we survey 20 households 100 different times. So in other words, you go and pick out 20, 100 different times. We would expect about 7 trials to result in 5 households that are wireless only. So where to get the 7 from is by taking this 100 right here and multiplying it times this number right here, the result. And that's what I wrote right here. And that's approximately 7. That's 6.56. Yep. So whenever they give you this number right here in 100 trials, you take that, multiply it times whatever your result was. And that number right here should match with that. Questions? Any questions?
Still a little bit confused about what C is in the equation.
It's a combination formula. It actually represents NCR. Normally it's N and R that's normally used. It's, uh, 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 and so basically it's how many different ways can you choose R out of N times. So it's like a whole nother lesson on what it actually really means. But we're not really focusing on what C means. You just need to know where it is in your calculator if you're going to use your calculator. So yeah, that's a whole lesson by itself on what C is. So so if you have a calculator and you want to see, want me to help you find it and stuff like that, then feel free to bring it one day and I can look at it. But yeah, but it's the combination or how many different ways you can take 5 out of 20, or you can choose 5 out of 20. Okay, okay, cool, cool, cool. That's good. Anything else? Anybody else before we go to B? All right, so let's look at B. So this one we're looking at fewer than 3 are wireless only. So before we had exactly 5. So 5 was the only number we had to worry about plugging into the formula. But this time we're looking at fewer than 3. So we're talking about 0, 1, or 2. So in other words, if I were to choose 20 families, what's the probability that 0, none of them will be wireless only? What's the probability of one of them be wireless only? What's the probability of 2 of them being wireless only? So we have to look at each one of those probabilities individually if we're going to just use our calculator. Like I said, there are apps out there wherein you can plug in a number, put 3, and they'll give you less than 3 and stuff like that. So, but right now, just making sure we know how to use it in our calculator since they gave us the formula, and we'll walk it out that way. All right. So we would have to do each one of them individually as far as putting them in the calculator, and that's what I did here. The 20 is the same. 0.41 is the same. Everything's the same except for the first one, I'm using 0 for the x. For the second one, I use 1 for x. And then for the third one, I use 2 for x. Any questions? Any questions? All right. So now putting those in the calculator, you get all three of these results, and then you go ahead and add them together, and you get 0.0028. All right. Any problems with that? Make sure we're okay with what we did. All right. Gonna scroll up. All right. So the next one says at least 3 are wireless only. So that's 3. And when you say at least, that means 3 is the least. And then we were talking about everything else greater than. If it said at most 3, then 3 would be the most. And we're talking about everything less than that. But it says at least 3. So 3 is the least. And we're talking about everything greater than 3. 3 and greater than 3. So that's what we have here represented. So we're looking at the probability of 3, probability of 4, probability of 5, all the way up to 20 and adding those together. So the reason why this one is good is because it emphasizes the importance of recognizing when you can do something easier in order to gain a larger answer. So if you think about the complement of that, is going to be everything else. So if you're talking about 3 or greater, everything else, which would be an easier find for us, would be 2 and less than. So you're talking about 2, 1, and 0, which is what we just found up here. So it's way easier to do that 3 times in your calculator, use the formula 3 times and find an answer versus trying to do it 17 times because you're going from 3 to 20. All right. So what we do is just take that 0.0028 and subtract that from 1, and that'll give us our answer. So that goes back to our complement rule. So your complement is always everything else. Any problems? Any problems? So even if we hadn't just found this, that is an option for you to do. Um, you just find the others and then subtract that from 1. All right. Any problems before we look at D? All right. So D, the number of households that are wireless only is between 5 and 7 inclusive. All right. So that's 5 and 7 and 6. So you're talking about everything in between 5 and 7, and also 5 and 7 itself when you say inclusive. So we're looking at those 3 probabilities and adding those together, 5, 6, and 7. And those are the formulas. All right. Put them in the calculator. You have those 3 values, add them up, you get 0.3381. Any problems? Any problems? See. Oh, hold on. Didn't need to do that. All right. Any questions before we go off of this page? All right. So that is it for chapter 6. So your third test is 5154, 51 through 54, 61, and 62. So let me look at this scheduling here. We got 1, 2, 3, 4. So, no, we said because we didn't do. No, we said we're supposed to be doing this as a proctored test. So Wednesday will be a review. Chapter. All right. All right. So we did 6-1, 6-2 today. Thinking one of these days would be the review, and then this day would actually be the test, which would be next Wednesday. Miss Andrich, are you saying something to me?
Yeah, can you hear me? The
I,
5th, I think, is closed for 4th of July.
oh, that's awesome. I was wondering if I hadn't looked it up, but if you're telling me, I believe you. So, thank you for that. So, well, that works perfectly then, because I was trying to figure out which day we use. So that works perfectly for us. Um, yeah. So if we're talking about doing our proctor test, that would be on the 7th, which is next Wednesday. Next class would be a review day, and you guys can ask whatever questions you want to ask. I'm not going to do anything new next class at all. So even if you aren't caught up with the homework, if you at least go into the test review and take a look at it, see if you have anything or have any questions on it. Um, and then when we meet on the 7th, that will be our test day. So what I do for the proctor test is that, how do I say it? And I think I got this written up. I'll shoot it to you guys in the email. So we come in on test day and it's proctored. So you make sure all of your cameras are enabled. Make sure you come with an ID and you show that to the camera and you leave Zoom up. Well, leave it on. You don't necessarily have to leave Zoom up in the window, but you don't close it out, in other words. And then you can go on to my math lab. I'll give you the password. You can go ahead and take your test. Um, Now, I will give you another opportunity to do better on it. I will provide a makeup on, but it would not be activated until after the test is taken. So after that day, so we take our test from 1 to 3, so probably around 3:30. the makeup opportunity will open up. So if you don't do your best on this test, there will be a makeup opportunity. The only thing about the makeup, the highest grade you can get on the makeup is an 85. Now, that does not mean I'm going to take 15% or 15 points from your grade, no matter what you score. So in other words, if you score 75, you get a 75. But if you score a 90, in all fairness to those who took it, who scored the 90 the original way through proctoring, the highest score you would be able to get is an 85. So that's how that works for the makeup. That's only for the makeup. But if you score, and the reason for that is that we have to create some type of, I don't say penalty, but some type of recourse, for this and make it seem like it's legit. But an 85 will not stop you from getting an A out of the course. I mean, so really, 85 will not stop you from getting an A out of the course if you do everything you're supposed to. If you average 85 with your test, you still will get an A. That's the lowest, test average you can average in order to get your A out of course. So if you do everything else, you still get your A. But it is a way to buffer it and to create the illusion that there's some type of, difference in taking the course, taking the test proctored versus taking the test just on your own. So that's why I have to do something of that nature. But once again, if you score 85 on your test, it will not stop you from making an 8 if you did everything else as far as your homework is concerned. But I will shoot, details on this process, to you guys in the email. But any questions on anything I've said up to this point? Make sure we're okay.
I just have questions for the I have the TI 83. I just want to know how to put those formulas in so I can wait till after.
Okay. Anything else, anybody else before I dismiss and then help her with her calculator? So once again, next class will be an open class. I will not do anything new. I will just be answering questions. So how long that class is will be dependent upon whatever question you guys bring to the table. If no one has any questions, then I guess it'll just be a high and bye type of thing. It's up to you to, take advantage of that. Me bringing the questions to the table, I found is not the best practice because this kind of makes people go in and say, okay, what do I know? What do I not know? Type of thing. And that's what I'm trying to, push here and try to get you guys engaged on that part of the process. All right. So anything else before we close out? Everybody good? Everybody straight? All right. So you guys have a good one. Be safe. I will see you on Wednesday and take care. Yes, that test would be on chapter 5, chapter 6. Yep. All right, Miss Andrich. All right, not a problem. All right, so now you were talking about using this formula right here. Okay, so now do you have a, well, first thing we want to look at trying to find that combination button. Do you have that, do you know what a combination button is?
Probably not.
Okay, so do you have a math button? Should just say
Yeah,
math.
I have a math button.
Yeah, so click on that and then scroll over to PRB, which represents probability.
Okay.
And then you should see NPR, NCR.
There's NCR and NPR.
Yep, so NCR is going to be that. So what you would do is, let's say if you were, trying to, let me take a picture of it so I can quote it exactly. And I'll have to keep scrolling up.
Man.
Come on. All right, so if I want to do the first one, we got 20 CP, not CP, C5.41. So let me write like this. If I can write it correctly. So you can actually put it in your calculator just like this and will give you that result. So it's just that you will put in 21st, then go to the NCR. And I forgot whether the N and the R disappears or not. I think it does. Some calculators leave it there. But I think yours disappears and just you're able to write it like that. Is that what you're able to do?
Ooh.
Okay, okay, it leaves it. Okay, so right, that's fine. So yours would be like that, and then you do parentheses. Make sure you come out of the you know, the NCR thing. So you probably might have to hit the arrow to the right to make sure you're out of it,
Okay.
and then put a parentheses, and then go ahead and put the 0.41 and close the parentheses. And now you're gonna look for this symbol right here. That should be to the right.
Yep, it's right under the
Okay,
clear button.
okay, cool. And then you can just go ahead and put 5, and make sure you hit the right arrow to come out of your exponent as well. And then go ahead and put the parentheses. Then you can just do the same thing, and then use that. But this time, parentheses is going to be up in the exponent, so leave that up there. 20 minus 5.
Okay, cool. That worked.
Okay, cool, cool. Yep,
Thank you.
not a problem. So let me know if you have any other questions about it, and then we go from there.
And then for the test, are we allowed to have like some of the formulas out?
Yeah, yeah, I'm not gonna take
Okay.
it. There's no way I'll be able to police that. So yeah, you're fine.
Okay.
So thanks for asking. All right. So if you're good, I'm good. Let's see if anybody else is up here.
Yes, sir.
All right, what you got?
Quick question. So, for test two is up, right?
Mm-hmm.
Taken.
Yeah, it should be up there.
Okay.
Yep. Let me know if you don't see it.
Okay. Yes, sir. Thank you very much.
Yep, not a problem. All right, anybody else? Ms. Williams, you good? Body straight, straight, straight. All right, you guys have a good one. Be safe, and I'll see you next class.